Great. All right. Thank you, everyone. So my name is Brian Helba, and I will be presenting an open source data archive for expert annotated dermoscopic images. Actually, if you'll forgive me, I'm going to try to get my laptop on the same page here so I can see my own presentation. Well, maybe not, so I guess I'll glance backwards. So I'm from Kitware. We are a company that provides open source toolkits and consulting to solve scientific problems. We're probably best known by some of our toolkits, maybe CMake, which is a build configuration system for C++, and also we have several other toolkits and applications that are pretty broadly used in the academic and scientific community. I'm from the medical department, so I'm going to discuss a problem in the field of dermatology, and then outline what we've done to sort of address that problem, and then hopefully talk a little bit about the tools we used and the various Python libraries we're using, and then maybe a little bit for future work, and I can elaborate on various things in question and answer if you'd like. So the problem is melanoma. This is a picture of melanoma. So this is, what would start out as, an ordinary skin lesion that maybe is a, strangely colored mole. And this is a particular image that's in a fairly advanced disease. It's probably not going to get much worse than this visibly, but once the cancer reaches the later stages, it will metastasize into your bloodstream and go to your organs and have all sorts of problems. So melanoma is one form of skin cancer, but is the most prevalent and the most lethal. Actually, I should say not necessarily the most prevalent, but definitely the most lethal that you would actually care about. This is a map of the prevalence of melanoma. The United States and Australia are particularly hard hit, partly due to the demographics and partly due to the fact that we get so much sun. If we manage to detect and treat melanoma early, the outcomes are extremely good. 98% 5-year survival rate. The problem is that because oftentimes people don't necessarily get screening, people don't realize that they have the disease. Often they wait until far more advanced stages when the outcomes are extremely poor. Less than 20% really if it's a late stage cancer. The best way to actually conclusively detect melanoma is a biopsy, where they make an incision and sample a small amount of the tissue. But you wouldn't know to do that unless you had apparent signs that there was a problem. And additionally, biopsies are invasive. And there's a huge cost issue there as well. You can't just do them on everyone who may have some risk. And in fact, in children, worldwide they perform on average about 500,000 biopsies per year to detect only about 400 cases. So if we can find other ways of detecting the cancer, or alternatively find a better pre-screening mechanism to determine who biopsies are appropriate for, that'd be really great. And there is such a tool. It is Dermoscopy, which is basically taking pictures of the skin with pretty much an ordinary camera apparatus and then a specialized lens that either uses polarized light or oil immersion contact lenses. And there have been a number of studies out there that show that this both increases the detection rate and reduces the unnecessary biopsies, so greatly increases the sensitivity and specificity of cancer screening if used as basically a first-line measure. The problem is, though, that dermoscopy, the camera is fairly simple. It doesn't require a trained dermatologist to operate the camera, but the actual interpretation of the images is very difficult. And there really is not a lot of consensus in the medical field about how to even interpret images. There are various schools of thought. There are various competing textbooks. In fact, I'll show you in a little bit a list of all the various competing terms that they have to use. So this is an area which really is ripe for computer vision to come in. And that would not only help to provide maybe some standardization of terms, but also can greatly increase the throughput. If you can have a nurse giving operating the camera, and then have some pre-screening techniques done by computer vision algorithms, that you can screen many more patients than if you had to have it an expert trained dermatologist review images one by one. There actually have been attempts to apply computer vision algorithms to the detection of melanoma. There's several books written on it. But one particular issue, as quoted here, is that the the problem is very difficult given the relative paucity of lesion data and consequently the low quality of training data available. So there aren't very many good images out there for computer vision researchers to train on, and there's also definitely almost a complete absence of ground truth information showing actually, where the lesion is, what particular features, visible features, correlate to, say, some, clinical outcome or clinical facts. So we've developed the ISIC Archive, which is a web-based tool to store images of lesions, clinical metadata associated with them, so things like the age of the patient, and also things like if that particular image was on a patient that later had a biopsy, what the results of that biopsy were. And then also we have tools within the site to produce annotations and associated ground truth information for these images that are at the moment being done by world-leading experts in dermatology. This work is being funded by the International Skin Imaging Collaboration Melanoma Project with mostly philanthropic funding, but we're also pursuing several NIH-funded efforts as well. And so this is completely open source code. It's available here on GitHub if you'd like to check it out, github.com/imagemarkup. We may rename that organization eventually, but we'd have redirect links anyway. And it's primarily a Python web application, so I'm going to try to stick to parts that are necessarily sort of server-side and algorithmic and sort of gloss over a lot of the client-side web stuff. So the archive basically operates as a pipeline model where we have several phases. The first is to upload images. Then we do some basic quality control to make sure there's no identifying information, to make sure that the images are clear, not blurry. Then we also pre-process the images to identify basically where the lesion is, regions of normal skin, and apply a superpixel segmentation, which I'll talk more about. And all of this pre-processing is in preparation to do the actual meat of the work, which is in what we call phase 2, where we have experts come in and actually annotate these images. And then the data stays in an archive available online, freely and permissively licensed, and publicly downloadable. And we have several tools so that researchers can actually download the images. The upload step is pretty straightforward. Just take some images, zip them up, and send them to the site. We automatically unpack the zip file, convert it to the proper format. We tend to use multi-resolution big TIFFs to store the actual images. We also have the capability to store CSV files and associate the lines in those CSV files with each particular image. I'll tell you, Python zip support for very large files has a lot of weird quirks. So if there are other ways of getting data into the archive, we're looking to support them. But the problem is a lot of our data sources come from individuals and institutions who are not particularly computer savvy. We're not necessarily have high bandwidth pipes from from an instrument being directly acquired. This is more old archives of images that happen to be laying around on some researcher's desk, and we beg them for access to it. And as part of that upload step, also we do some basic anonymization. To scrub metadata, we're looking into actually some techniques involving OCR to see if we can find also if there are any markers or text that are embedded in the images that we need to recognize and either blur out or cause the image to be flagged. At the moment, all the review is manual. We just get a list of all of their various images, and one of our associates goes through individually and just reviews all of them and makes sure there's no tattoos, there's no embedded timestamps or anything like that would compromise the anonymity of the patients. The next step here is the lesion segmentation step. We basically have two operations. A user will click on where they think the lesion is in this image, and a segmentation routine on the server will automatically be run. We basically take the image, encode it in NumPy, send it off to OpenCV, apply a flood fill algorithm, a contour detection algorithm, and then we ultimately convert that to a polyline. We were for some time trying to smooth the contour surrounding the lesion. But we found, honestly, it was a lot of work to tune the smoothing to be exactly, right, and it wasn't actually providing that much value to people who were consuming our data. And then ultimately, the lesion boundaries is encoded as GeoJSON, which we really like as a way to store, coordinate representations of all kinds, and then is sent back to the client. We also have the user identify regions of normal skin. And then the next part is, and let me preface this. So typically in computer vision, when you do ground truthing, you maybe draw a bounding box around objects of interest. The problem with this is there's a high degree of random variability in this. You can be off in one direction by 1 pixel and not know it. There's a huge amount of variability, and also it's not necessarily very precise for highly contoured regions. It's great to draw a square box, but you're not going to draw very sophisticated polygons. So we apply superpixel segmentation. We use the SLIC algorithm, the simple linear iterative clustering algorithm, to basically generate cells of similar color and intensity within these images. The user basically has control over the tolerance, changing the size of these until they are satisfied that basically you have homogeneous regions. And then these are encoded as basically a label map and with PNG, just because it's a nice encoding scheme. So the next step is feature annotations. This is a list of some of the features that clinicians use to describe lesions. Here's some more, and this is not all of them. So rather than try to resolve this problem ourselves, we're basically just inviting leading dermatologists to come in, express what they think of these images, basically using sort of a paint-by-numbers approach. So they can select the particular feature that they're interested in, select the confidence that they have. We have sort of 50 or 100% confidence as to whether that feature is actually present, and then just click and drag and wave the mouse around the image and select regions that have this particular feature. And actually, in practice, we've noticed that there is a large amount of variability. This is 3 different clinicians all annotating for the exact same feature, and these are the different regions that they came up with that they believe this feature was present in. And then finally, to export it, we have a nice RESTful API documented with Swagger, and the framework that we use automatically does this documentation for us, and then you can easily use your operations to fetch the data. We also support, for the benefit of some of the epidemiologists and other less technical researchers, the ability to dump the data out directly as, say, a CSV. But by the way, all of our data we encourage it to be licensed as CC0, so it's fully publicly available. In some cases, the data sources prefer it for it to be Creative Commons attribution, but those data sets are fairly limited. And I don't know if I mentioned this, but we have about 13,000 images in the archive so far, but we've only recently begun accepting images, maybe about 6 months ago. So finally, I want to talk a little about the tools we use. We have a very nice deployment process. So in theory, you should be able to, if you have Vagrant and Ansible installed on your machine, and I guess a provider of some sort like VirtualBox or an Amazon account, you should be able to clone our repository, go in, say Vagrant up, and it will spin up a brand new machine, install all the software, install all the dependencies and everything as necessary. We use mini Conda actually as a base environment, and then we get Conda packages for things like OpenCV, which are very difficult to install on your system and impossible to install with pip. There's actually, if anyone uses Ansible for provisioning, there's a third-party module for Conda management with Ansible that I've made some improvements to, and I'm going to try to get contributed upstream. So if anyone would find that useful, if you use Ansible, if you use Conda, come let me know, because I'd like to get some feedback. The server that we use is Girder. This is a performant web framework for basically large data sets and archives. So it actually comes with a pre-built server that allows you to just install it and start uploading images directly, but it has a fairly sophisticated plugin system that we actually use to do a lot of the customization and the automated tasks. And it uses a number of Python libraries. And actually, it's fairly well tested, has over 90% code coverage. Internally, we use Celery to manage a lot of the long-running tasks. Like I mentioned, NumPy and Python OpenCV to do a lot of the image processing. IPython Notebook has been really nice for just debugging things and exploring our data. But I definitely want to make some better use of it for more user-facing things as well in the future. Here's some more front-end technologies. This is more web stuff. And in terms of future work, we definitely, first of all, like to explore this phenomena that we have such disagreement between annotators. Number one, to characterize it and sort of quantify it, and we also have noticed that in many cases there's a lot of intra-rater variability. So if you give the same image to the same clinician 2 weeks apart, they may actually give you a different answer. Or if you take the same image and flip it upside down, and in this particular case, orientation doesn't matter when it comes to skin lesions, we notice that sometimes we get different results, and we definitely like to explore this. We'd also like to explore a method for basically dealing with what's called disconcordance, where you have disagreement among experts, and see if there's some way we can come up with a consensus. And if we can come up with a consensus, can we then train non-experts to perform this task? because it's extremely time intensive to get, clinicians with 20 years of experience to sit down and annotate hundreds of images. So if we could train non-experts, that would be extremely helpful to generate future data sets. And also we're working with some people at IBM Research to automate the detection of the lesion boundary in normal skin. And they're probably one of the first consumers of our data sets. So I'd like to thank these various organizations. We're sponsored by ISDIS, which is the philanthropic organization which has commissioned this. And we've also worked a lot with Memorial Sloan Kettering, where most of our clinicians are. A guy named David Gutman at Emory University is sort of the, this was his idea. Kitwares provided most of the software support, and Rich Stoner helped also with some software support initially. So, are there any questions? Yes.
Yes. Oh, yeah.
Oh, I'm sorry. Hey, there's one right here, but I'll.
Just curious why you, if you thought about using Kitware's own Midas repository.
So yes, so Girder is essentially Midas 4.0. Midas is written in PHP, and in my personal opinion, is a little bit difficult to develop plugins for, and also it's not really fully RESTful and well abstracted between this client and server. So Girder is basically a reimagining of Midas. So if you're familiar with that as a data management platform, Girder is sort of the new wave of that, and that's where all the new development is going into. So we were sort of early adopters of Girder almost a year ago, and at this point it's definitely mature enough to where we can use it pretty painlessly. Yes.
So in one of the slides you said that the user is iterating. That's the last line of the slide.
Oh.
That the user iterates the step definition, the boundary definition, or does he go to the next image?
Oh, sure. Yeah, I'll definitely go over that real quick. So particularly for detecting the lesion, the process is you click a point and you select a tolerance, and then the boundary is generated automatically. And then the user may iteratively adjust the tolerance, which will basically concentrically expand outwards or inwards until they find that they actually have identified the edge of the lesion. And the same thing for the superpixel step. You're able to modify the tolerance until you find a value that you believe has some homogeneous regions.
So you only have one user looking at one boundary.
So for the pre-processing step, to identify the lesion boundary and the superpixels, yes, we only have one user. For the annotation step, we potentially have multiple users and multiple different studies with different sets of features and different parameters. There's one back there, but yeah.
Okay. So one of the slides you showed that had all the grid of images available to choose from. Yeah. Have you attempted any white balance as a pre-processing step? Because color is hugely important to the dermatologists.
Yes, absolutely. So at the moment, we're attempting to sort of not wade into that because we don't want to necessarily be accused of biasing these images. So we present the images as they are, and in fact, we have criteria for things like the size of the monitor, how far the user is to sit away from the screen, and things like that. If we wanted to start, getting our own hand into post-processing these images for image quality, we could, but we might have some people who object that the clinical fidelity is sort of being compromised.
So you mentioned that this is not just a problem in the US, but in Australia, in the UK, and parts of Europe. Do you get images submitted internationally? And if so, how do you obey the medical bureaucratic constraints of anonymity and license issues?
Sure. So we require all images that are submitted to us to be already de-identified and anonymized. This quality control step is basically a supplemental measure to basically ensure that there are no things like tattoos, or there occasionally are fiducial markers, which are like rulers that maybe might have some information. We require all the information to be anonymized. We also require contributors to sign a license agreement stating that it is either CC0 or CC BY. Yes?
I guess two questions. First, that plot that you have that shows the US and Australia.
Sure.
Is that prevalent in those two countries?
This is prevalence, yes.
To access the screening, or is it actually demographic?
So this is prevalence in those countries, right? So in fact, if you look, I don't have a plot here of mortality, but if you do look at mortality, it definitely shifts then because of access to both screening and treatment. So countries like, particularly in Southwest Africa, which don't look like it's that prevalent, actually have very high incidence of mortality. The U.S. and Australia still have reasonably high mortality. It's probably maybe the number 3 cancer killer of all the cancers. That's difficult to quantify, though, because even what the definition of cancer is somewhat loose. But it's definitely primarily an issue that we want to do screening for, and hence dermoscopy in the U.S. and Australia. In countries like in Africa that maybe have a decent amount of incidence, but it's much more difficult to screen for because it tends to come in more advanced stages quicker. Dermoscopy is not quite the tool that it could be, and also just because of access to healthcare resources, you're not going to have as many pre-screenings with dermoscopes.
So the second part of that question is, given the significant contrast between normal skin color and the cancer,
Sure.
why do you still need, I guess, what's the restriction you're running into for automatically identifying and segmenting? Why do you still need human interaction?
Sure, great. So these are all skin lesions, but not all of these are cancerous, and not all of those are melanoma, and not all of those are actually a problem where they will progress. So there are lots of skin lesions. There are a number of different criteria for identifying when something is potentially melanoma and when something is a dangerous melanoma that should be actively monitored or biopsied. But there are all sorts of strange and funny-looking skin lesions that people have that are absolutely no clinical concern at all.
Do you do time series on them? 'Cause I would imagine progression of melanoma a lot.
So that's absolutely the protocol for high-risk patients. If you have something that they've perhaps biopsied and the biopsy results were inconclusive or negative to the point where they didn't want to remove the lesion, but they were very concerned that it may progress to become melanoma, the protocol is absolutely continuous monitoring, and maybe come back every 4 weeks and have it photographed for change, because change is one of the hallmarks of a fast-growing deadly lesion. In our particular case, though, because we're attempting to provide a data set for ground truth and training, we haven't so much worked on time series data, although, again, if the computer vision researchers who are partnering with say, hey, we'd like to start to do change detection, and basically longitudinal analysis of a data series, yeah, we definitely might want to start soliciting contributors of those images and annotating them. Yes?
Given those time series, what would your approach be to registering them? Since getting an image 4 weeks apart, or a series of images that are 4 weeks apart, they're obviously not going to line up.
Yeah, it's an interesting problem, and it's definitely something that I think we have a decent amount as a field, and I personally have done a little bit of work with also internal lesions in, say, CT data sets, where you have a longitudinal series of someone, say, on a clinical trial, and you have CT scans of them every 4 weeks over an 8-month period. And the answer is, at least in the radiology and CT field, you don't really try to do an explicit mapping of every point to point like you would of say a scan against an atlas, but you do, for the convenience of the radiologist or the viewing clinician, maybe reorient them and overlap them. But actually, it turns out clinicians are very good at sort of doing that in their head. So that's what's going on in clinical practice. In terms of computer vision techniques, it really depends on what our researchers ask for, whether they need us to do any pre-processing. But I don't imagine that's a particularly difficult step to just do basically a rigid, translate, rotate, zoom. I don't think we need to do any sort of deformal registration because these are growing, these are, changing. So it's unlikely that you're going to get good results there anyway. Yes.
Parts of the body that are excessively heavy.
Yes.
Has there been any barriers to diagnosis or identification in those cases?
So for clinicians, no. But for computer vision researchers, that's a good question. And we have some preliminary results that we haven't had any complaints yet, but we'll definitely have to look. I mean, so at the moment is, we want to provide a very, granular access to these data sets and continue to publicly host them so that if you do run your algorithm and you do notice that certain, cases you have a very difficult time, processing and actually successfully identifying the features on, you can go back to your image and look at it and see, oh, maybe it's because it's hairy. But at the moment, it's just sort of data that goes in, data that comes out, and we just treat it as a black box.
It seems like a fairly robust framework. It hasn't been applied to any other fields.
Yes, so actually, we have some efforts right now at Kitware to actually take sort of the same framework to apply to a number of different imaging modalities. We have pathology data from microscopes that we're putting into this. We have a number of other efforts at Kitware to handle that already that is going into Girder. So we're partnering with a few medical schools and hospitals actually right now to host a lot of their histology and pathology data for education and remote consulting. We also have some upcoming efforts dealing with radiology archives and with archives of pathology, there's microscopy, genomic, radiology, and clinical history metadata, all basically take these four data types together and build sort of an archive of cancer samples for use in research. So to be able to look at a particular specimen of cancer and see a CT scan of it, an MRI scan of it, a slice of it that's been stained under a microscope, the history of the patient, and a genetic profile, all in one sort of data source that we hope will also drive a lot of research in the future. So that's not related to this effort, but those are other things that we're doing at Kitware.
All right, well, that concludes our session. Thanks, everyone, for your participation and to the speakers as well. Thank you, Brian.
Great, thank you.
See you in the afternoon.